Thank you. Calories per gram degrees Celsius. Change in temperature, well, that's whatever that final temperature is minus the initial temperature, which is 60 degrees Celsius, plus mass of the water, which is 25 grams, specific heat of the water, which is 1 calorie per gram degrees Celsius. Change in temperature, which is whatever the final temperature is minus 20 degrees Celsius is equal to 0. Now, putting the units in there just sort of clutters it up, but from a science point of view, the units do matter. However, we've now made it a math problem, so let's just write down the math problem here. I have 50 times 0.215 times t minus 60 plus 25 times 1 times t minus 20. That's the math problem. I do want to point out that our unknown, the TF here, my final temperature, it's the same for both. The aluminum is going to cool down until it's the same temperature as the water, or the water is going to heat up until it's the same temperature as the aluminum. This one I can do in my head. That's 25. And that one is 1.075? No. 10.75. Minus 16. So now we distribute. So I have 10.75 T minus whatever that is times 60. $645. Okay. Plus 25 minus 500. Oh, 25T. Lost. Distributing. So we have 35.75 times the final temperature minus 1,145 is equal to 0, or 35.75 T equals 1145. Divide by 35.75. Now, before we actually write down the answer, some of you, at least one of you, I suspect, has actually done it already, but from what we talked about earlier, I know the final temperature has to be between 20 and 60 degrees Celsius. It has to be. And because the aluminum gives up heat, or gains heat, the temperature change requires less energy transfer, we expect the final temperature to be closer to that of water. So whatever it is, it should be between 20 and 60, and it should be closer to 20 than to 60. So it gives us a quick, dirty look at, does our answer make any sense whatsoever? And we end up with 32.2. 30.02.
32.02. Yep.
32.02. All right. At least I knew I heard a 2 in there somewhere. Units?
Degrees Celsius.
And this, in essence, is what you're going to do in the lab. The difference between this and the lab, I mean, you're going to take water, you're going to put a cube into boiling water to get the cube up to the temperature of the boiling water. Then you're going to transfer it into cold water, checking the temperature of the water as you go, and you'll So the temperature of the water should be increasing, and then it'll peak, and then it'll start cooling off because we don't have our perfectly insulated material. But you'll be looking to see where it peaks. And then from that, you're actually going to be solving for this. Since you'll know the final temperature, but your unknown is going to be the specific heat of the material. And then you'll compare it to the bulk value. So, questions? Make sure this thing didn't shut off. Oh, still going. All right, so let's actually work through one that is closer to lab-like. We'll keep aluminum. Since this is going to be sitting in boiling water, it's going to be really close to it'll be close to the boiling point of water. And you know what? Instead of aluminum, we're just going to make this some unknown. Because I'm about to make numbers up, and I doubt if I'm going to get close to 0.215. So initial temperature of the metal. So instead of aluminum here, I'm going to put a little M for metal. So we have a piece of metal that's really close to the boiling point of water. We put it into our room temperature water. And the final temperature is 37 degrees Celsius.
So is that the final temperature of the water and the cube?
Yes, because the temperature of the water should be increasing as long as the cube is giving up heat. And then then when it peaks is when basically they're the same temperature,
Okay.
or close enough. Now do note from a mechanics point of view, I got a cube in boiling water. The temperature of it's been sitting in there for a couple of minutes, so the temperature of the cube is close enough to the temperature of the boiling water. When I transfer it, it will immediately, as soon as I bring it into the air, it'll immediately start losing energy into the air. So you need to transfer it as quickly as possible into the other water and cover up the other water as quickly as possible. So we have 50 grams times our specific heat of the unknown times the change in temperature, which is 37 minus 99 degrees Celsius, plus mass of the water, just 25 grams, times specific heat of water, 1 calorie per gram degree Celsius, times change in temperature of the water, which is 37 degrees Celsius minus 20 degrees Celsius, equals 0. I should have picked a number where the math was easier, but I will. So that's negative 62. And that is 17. Negative 3100 C plus $425. That's right. And so my specific heat, we subtract 425 from both sides and then divide by negative 3,100. Point zero. What is it?
137
137 units.
calories per kilogram degree Celsius. Or grams, sorry, I don't know why I wrote those down.
I'm sorry, I didn't write down kilograms because you said it and my mind was so focused on
I
grams.
wrote down kilograms too, I don't know why.
Because you don't like decimals, you just hate decimals with a passion. So if you want to do kilograms, then you'd be multiplying by 1,000 grams per kilogram, so this would be the equivalent of 137 calories per kilogram degrees Celsius, if you wanted to do away with those pesky decimals. Now we can make this slightly more generic, and in the lab I do this. Basically we're solving for this right here. So you subtract this whole thing over to the other side, so we have mass of the metal times C delta T, C of the metal, delta T of the metal is equal to negative mass of the water, specific heat of the water, change in temperature of the water. And then we divide by the mass of the metal, the delta and the change in temperature of the metal. And so the specific heat of the metal is that right there. I think that's the way I have it written. It's also possible that I went ahead and just substituted a 1 in for CW. But I think I left CW there. So basically the math behind the lab. All right. I'm assuming someone would have asked a question if you had one, though. That long dramatic pause there was for questions. All right, so let's take a look at the actual cooling process. We're going to change it around slightly because in this situation, any energy lost by the aluminum went into the water. The water was enclosed. There was no energy lost into the big environment. Let's change it slightly, and now we're going to put the hot piece of aluminum into a really big open space or into a big pool of water, something where the amount of water is vastly larger than the cube. In other words, one where the temperature of the water is not going to change significantly because you have so much water, the energy gets spread out over a lot more particles. Personally, I always picture it as a hot cube put in the middle of the room. The average temperature of the room is not going to change significantly because I have a small piece of hot metal sitting in the middle of it. So I will start it out at 60 degrees Celsius. We'll keep it as aluminum. And 50 grams, although the 50 grams is not particularly significant here. Into big open space. After 10 minutes, the temperature is now 40 degrees Celsius. And I just made those numbers up. I know it's cooling down. Put it in big open space, I do need to tell you that's at 20 degrees Celsius. Question is, after another 10 minutes, what is the temperature? It is not 20 degrees Celsius.
0.
No. So this gets into what's known as Newton's law of cooling. And you'll be able to see this on Friday. It's not part of the lab, but you'll have a thermal probe in the boiling water. And then you can just take the thermal probe out of the boiling water and set up the LabQuest so that it will record the temperature, and you can see how the temperature changes. So if this aluminum is at 60 degrees Celsius, and I'm putting it into a big open space at 20 degrees Celsius, and again, big open space indicating that, or implying that this number is not going to change any. What is the coldest that aluminum is going to get? What is that? The minimum temperature.
20?
Yes, it will not get colder than the room. As with all thermodynamics, you should always tack on, statistically speaking. So my aluminum, the temperature of the aluminum, in degrees Celsius, we start out at 60. 20 is the bottom. It's the absolute smallest it will get. What Newton claimed is that it will get closer and closer. At some point, we can't differentiate it, but it actually curves as it gets closer and closer. This is an asymptote. And he makes the claim is that the aluminum is going to lose the same percentage of temperature in the same time increment. So let's think about that. So the first 10 minutes. What was the change in temperature of the aluminum?
20 degrees Celsius.
Technically negative, but we don't have to worry about the negative signs would all cancel out. What is the maximum amount of temperature that it can lose?
After 10 minutes?
No, I mean, it starts out at 60, and it's going into a room at 20. What's the maximum it could possibly lose?
40 degrees Celsius?
I think two of you said the same thing.
40.
Sorry. Yep, 40. And it bugs me that I hear other people's voices, and some people are not getting mental credit for speaking up. I recognize Manal's voice, and then after that, there's just
loud.
Yeah, it helps. Back to the student 2 summers ago. Really bad volume control. It's almost like he was shouting everything, but I heard him clearly. I knew who was speaking. All right, so what Newton is claiming is that in 10 minutes, assuming that information is correct over there, in 10 minutes, I'm going to lose that fraction. I'm going to lose half of what I possibly can lose every 10 minutes. So second 10 minutes, the temperature is now 40 degrees Celsius for the aluminum. What is the most it can lose?
10 degrees?
20.
You jumped ahead. Yeah, the most it can lose is 20. The actual change in temperature is, well, we've got a fraction here. That's where the 10 comes in. So after another 10 minutes, this is now 30 degrees Celsius. We can keep going. The next third 10 minutes, well, I know it's going to lose half of what it can lose. So what's the most it could lose? We're now at 30 degrees.
15. You said half?
It's not half of that number, it's half of what it possibly could lose.
Okay.
It's now 30 degrees Celsius in a room that's 20 degrees Celsius.
10.
So it could lose 10 degrees Celsius. Again, that's the maximum they could possibly lose. And so now the change in temperature is 5, not meters per second, 5 degrees Celsius. So it's gonna lose 5 there, so now it's gonna be at 25. And it's gonna lose half every single time, given my initial setup. So after another 10 minutes, it'll be 22.5, and then 21.75. It just keeps getting closer and closer. In this nice ideal situation, it never actually gets there. But at some point, it becomes indistinguishable. So if I had some sense of plotting properly here, let's see how well this will actually show up. So these will be 10-minute increments. So time in minutes. So 10, 20. Okay. I am going to take an attempt to do that a little bit better. At some point, I'll just give it up. So at time 0, it's at 60 degrees Celsius. At 10 minutes, it's at 40 degrees Celsius. At 20 minutes, it's at 30. 30 minutes, it's at 25. 40 minutes, it's 22 and a half. And logarithms are involved if you actually went into the calculus of it. Or exponentials, depends on how you want to look at it. All right, questions to hear? Now, one of the problems in the textbook that Hewitt gives, unfortunately, he picks numbers. It's one of the assigned problems, but he picks numbers where if you don't know what you're doing, you can come up with the same numbers several different ways. And it's sort of misleading. That's why I like to use numbers where there's not a lot of duplicates there. It's unfortunate that that happened right there. So let me come up with, let's do it again, come up with numbers that are not going to work out nicely, or that won't duplicate, I should say it that way. So let's make that 50. We'll keep that at 20. Oh, nope, sorry. That's 60. That's 50. So I want you to predict what is the temperature after that second 10-minute interval. I'd like you to sort of work on it on your own, at least set up. If you don't have a calculator, just set it up. If you do have a calculator, just come up with an answer. Assume you have an answer. Yes. That's the fraction it's gonna lose. Actually, oh, wait a second. It's how much it loses divided by the total amount it possibly could. So it's not, how much does it actually lose in the first 10 minutes? Yeah, so the numerator is 10. And the most it could possibly lose.
Oh.
Not 50. It's the most it could possibly lose, so it's the difference. So it's 40. That's so far so good. Yep. So it should be the amount it actually does lose divided by the total amount it could lose. Something went off there. So that's the refraction there. So now it's this temperature. The most it could lose is the difference between those two numbers. Yeah, so it's something like 30. So that's the constant.
Okay.
Okay, did I just divide these two numbers?
All right, so it starts out at that temperature right there. What is the most it could lose? Yes, so it'd be, so that loses actually 10. But the most it could lose is 40, so that should be 10 over 40. All right, and now for the next 10 minutes, delta T is your unknown, but now you're at this temperature, what's the most you could lose? Yeah, the 30 down there. So that's what, so you basically have that equal to this. Solve for delta T. Alright, so your math is set up right. Alright, so good with that. That's, so you're multiplying what it possibly could lose. You don't multiply 50 times 4, you multiply, once it's at 50, what's the most it could lose?
Oh, so each section would be different?
Yes.
Okay, it wouldn't be, okay.
You're still gonna multiply by a quarter, but you're not multiplying the temperature, but the difference between what it is and what it could be. Yes. One quiz or test, don't forget quiz. set up this, so it's gonna lose, that's basically a quarter. It's gonna lose a quarter of what it could lose every time. So, at here, you could lose 30. So this delta T over 30 should be equal to 10 over 40. So it's gonna lose the same fraction each time. So you would set that equal to that, solve for delta T, and that's how much it loses. That should be equal to this.
But at this point, it's only 30.
Right. So 10 over 40 equals the change in temperature over 30. All right, so now that you're here, you're at 50 degrees. The most you could lose is 30, all right? So the fraction is the same every single time.
Okay.
So 10 over 40 equals delta T over 30. Yep, that's right.
Okay.
Don't forget units.
Yep.
All right, so that's the change in temperature. Oh, and there you go, the actual temperature. Yes. I mean, people are really close here, so let's take a look at it as a group. So the actual loss the first time was 10 over a possible 40. So that fraction should work for the rest, for every 10-minute period here. And so then, the most you could possibly lose for the next 10 minutes is 30, because you're now at 50, the difference between these. And so delta T is 7.5 degrees Celsius. And so you're losing, so